Hi everyone, welcome to our second video where we're going to be talking about regression using categorical predictor variables. In the previous video we were talking about how we can actually calculate a slope and an intercept in ordinary least squares regression when we're taking a continuous outcome and regressing it onto a categorical predictor. In this video we're going to be focusing on model fit statistics and the variance explained in the y variable by the x variable. So as a reminder, we're using this SAT prep course example where we've got 10 hypothetical students who took an SAT prep course and 10 hypothetical students who did not take it. Then we have their SAT scores. And if we plot those data as a scatter plot, there's SAT scores on the y-axis. We have people who did not take the course over here as the white dots, people who did take the course over here as the red dots, and then the best fit line, which we calculated in the previous video, running through those data points here. Now, as a reminder, we're looking at this using a contrast-coded version of the variable, right? Like we said, we have to take that categorical factor and assign numerical values to the different levels. So in this instance, we're using a contrast code where people who did not take the course get a -1 and people who did take the course get a +1. In reality, you would probably just graph this as a discrete categorical variable on the x-axis, but to reinforce the fact that we're actually recoding those categories as numbers, I'm plotting it with the values of the contrast code on the x-axis right now. So next, right, we said that if we want to actually test the efficacy of this SAT prep course, we can calculate an independent samples t-test by fitting a model where we make a conditional prediction, right, and we say we'll allow our prediction of y to change as a function of x. So we're estimating a line that has an intercept, right, and a slope, and we end up getting this prediction line here. And then what we're comparing that to is a null model in which we assume that the true value of the slope is actually 0. And then we want to say how different was the slope that we observed relative to the value under the null hypothesis, right? And we talked about how we can do this with treatment coding or contrast coding. That's going to change the actual value of beta that we observe, or the slope that we observe. But it's not ultimately going to really change the variance explained. And we talked about how regardless of if we used a contrast code or a treatment code, the R² for this regression was the same. So the coding is going to affect the individual betas and the estimates that we obtain, but the coding is not actually going to affect the model fit statistics or the R². So let's think about model fitting here a little bit more. So in our null model, remember that we are saying that the true relationship between x and y is equal to 0. So we could think about that as 0 times x, but those terms obviously will cancel out, so it's going to go away. And our null model then is just predicting y as a function of some constant, and then each person also has an error term. And as we've discussed before, right, if we only get one value, the number that provides us with the smallest sum of squared errors is the mean of that variable. So for our null model, right, our y hat, what we predict for each person is just going to be the average y. We can then calculate the difference between each person's score and the average to end up with an error score, right? And we'll have some negative values because some people are below the mean, and some positive values because some people are above the mean. And then if we want to calculate the sum of squared errors, right, to get the total variance in y, how much does y vary around its mean, we could calculate the sum of squared errors total, where we take each error, we square it, right, and then we add them all together. So in this final column, all I've done is I've squared these errors, and then if we sum all of those values together, we'll get the sum of squared errors total, which is 19,980, and that essentially becomes our benchmark. That tells us how much variance in y is there. How much does y vary around its mean? Now we can look at the reduction in that sum of squared errors to try and decide if we think x is a good predictor of y or not. Because if x is a good predictor, then we should reduce the amount of error that's left over when we base our predictions on x. If x is not a good predictor, then the SSE of the residuals of our regression model will be pretty close to SSE total. Because if x isn't a really good predictor, it's probably not all that different than just using the mean value of y. So now let's look at error fitting in our alternative model. So remember, in this model, right, we're going to get an estimate of an intercept and a slope based on how we've coded the x variable. And in this example, we've contrast coded the x variable. So that means that 0 is between the two values of x, because if you took the course, you get a 1. If you did not take the course, you get a -1. So 0 then is the average between the two levels of the variable. So remember, our intercept is always going to be the predicted value of y when x is 0. So in this case, it's 591 because that's the average of the two group averages. And then our slope is going to be 14 because when we've contrast coded this x value, a 1-point increase takes us from the average and puts us into the course group, and a -1-point decrease takes us from the average and puts us into the no course group. Right? And you can see that here in our model's predictions for this alternative model. If you were in the course group, this model is now going to predict 605 points for you, and everyone in that group gets the same prediction. Right? And if you were in the no course group, this model is going to predict 577 for you, and everyone in that group gets the same prediction. And again, right, 605 is the mean of the course group. So our model is predicting the value that will give us the smallest sum of squared errors in this group. And 577 is the mean of the no course group. So our model is predicting the value that will give us the smallest sum of squared errors in this group. So what we're interested then is calculating sum of squared errors for the residuals from this model, and how different is it from the sum of squared errors total we got before. So the sum of squared errors of the residuals are the same, right? We're going to take each y and compare it to its predictions. So for everyone in the course group, we're going to take their actual value, compare it to 605, and get a difference. For everyone in the no course group, we're going to take their actual value, compare it to 577, and get a difference. Some people will be below that estimate, some people will be above that estimate, so we can square the errors to make sure that they don't cancel out. And then we can add up the total sum of squared errors, right? And this tells us then how much of y remains unexplained after accounting for the variation due to x. And in this case, the sum of squared error of the residuals is 16,060. So that's a reduction, of about 3,000 points. But how big of a reduction is that in terms of squared errors? That's the thing we need to figure out. So we'll walk through the math of actually making inferences about this. But again, let's just visually compare these two models. Right, so we have our null model where we're predicting y, and we assume that the true relationship between x and y is 0. So in that model, we're saying there's a flat line, and that's our prediction for everyone. If we take all of the deviations away from that flat line, right, the sum of squared errors total is 19,980. If we fit a model and we allow that beta 1 to vary, right, so we don't force it to be 0, but we allow it to take the best fitting slope in the data, in this case, and given the way that we've coded our variable, that happens to be a slope of 14, and that leads to a reduction in the squared errors, because now the sum of squared errors of the residuals is 16,060. So that's a reduction of almost 4,000 squared errors. So that seems pretty big. It seems like we're getting a better prediction if we allow this line to tilt, right, and have a slope, than if we force this line to be flat. But how do we actually quantify this? Well, the way we actually quantify this and decide, is it a statistically significant reduction in the variance, right, or is it an impressive reduction in the variance, is using an analysis of variance. And the analysis of variance table is a very nice way of summarizing all of this. And it is very common across different stats programs and textbooks. There might be some variation in exactly how this table is presented, but you will almost always see some variation of this table anytime you conduct an analysis of variance. So again, we have our total variance at the very bottom, right? So this is if we just estimate the mean, what's the total variability in y? We have the variability of the residuals. So in our regression model, how much of y remains unaccounted for. And then, just by subtraction, we can actually process this to then say, well, how much of y was accounted for by x? Because if this is the total variability in y, this is how much was accounted for, then the difference is how much was actually explained by x. Each of these will have their own unique degree of freedom, and then we just divide across these rows to get the mean squared error explained, because this was the sum of squared errors, so we divide it by the number of parameters to end up with a mean squared error. And we can then calculate an F value, and that F statistic has its own distribution that allows us to calculate a probability. And we're going to get into that more in the future, right? For now, just know that the F statistic is another statistic, kind of like the t value, but rather than being used for sample means or sample standard deviations, the F value is something that we can calculate for a reduction in variance. And we can say, well, how much variance do we expect to be reduced due to sampling variability alone? And if we reduce more variance than we would expect due to sampling variability, then we think there might be something systematic going on, and we would reject the null hypothesis. So chopping up the total variance into these different sources is all that we mean by analysis of variance, which then ultimately gets abbreviated as ANOVA. And when we do an ANOVA, what we're interested in, how much variance was there total, how much variance did we explain, and how much variance is left over. And there are lots of different ANOVAs that you can do, right? And like I said, stats programs will present these things in slightly different ways. Here's my, the by hand calculations from the ANOVA table that I presented in the previous slide. Here's what the regression output looks in a statistics program like Jamovi. R gives you a similar ANOVA table, SPSS gives you a similar ANOVA table, but you can see that Jamovi tells us about this omnibus ANOVA test, where we have the sums of squared errors. It talks about it for the effective group. I labeled it as explained by the regression, right? But it's the effective group in the regression is explaining 3,920 squared errors. And then what's left over is 16,060, right? So those numbers agree, even though they appear in a slightly different place. And then when we want to calculate the R squared, right, to say, well, what proportion of the variance in Y was explained by X? We'd take the total variance, and we'd take the variance that's explained. We take the ratio of those two numbers, and we explained about 20% of the total variance in Y. So now there's also a lot of things on here we haven't discussed yet, and these are things that we're going to get into in the next couple of modules. We've not discussed the F statistic and its distribution, and we're going to be talking about that in more detail as we add variables to our regression models. But the main takeaway right now is that the F statistic is a lot like the T statistic, but unlike the T statistic where we're talking about the distribution of sample means or the distribution of sample slopes, the F statistic provides a formal test for the explained variance. Additionally, when we talk about the calculation of these different types of variance, there's going to be an issue when we add variables into our model. So like you can see here, it says note type 3 sums of squares. We haven't explained what that is yet. That's going to come up in another video, right? And there are actually 3 different types of sums of squared errors, and we'll talk about each of them, right? So we're going to cover these things in more detail. But right now, I just want you to really think about these sums of squared errors and how we can get them in our regression model. And then we're going to worry about all the statistical inference stuff and the different types of sum of squares in subsequent videos. And again, much like the conclusion of the last video where we said the independent samples t-test is really just, a particular case of the general linear model, analysis of variance is just a thing that you do with regression models. So you'll often in undergraduate stats classes see ANOVA as a separate type of analysis from regression, and people think about these things very differently. But in reality, the analysis of variance is a thing you do to the output of a regression. You can analyze the variance of any regression. So, as one of the things we'll show in the different videos as we go along, is that it doesn't really make sense to say, I did an ANOVA. What matters is what kind of ANOVA you did. And things that have common names in the literature, such as a one-way ANOVA or a multifactorial ANOVA, are all just special cases of regression models. But at the end of the day, they're all regression models, and we're always going to start by figuring out what's the total variability in Y, and then how much of that variability is getting explained by our different factors.